Hello everyone, and welcome to our session on time complexity of arrays. In today's session, we'll cover the fundamental operations performed on arrays and discuss the basics of time complexity. We'll also compare arrays with other data structures to understand when and why arrays are the best choice. As a visual reference, please take a look at the animation on this slide that shows a basic array structure with its indexing scheme. Let's begin. To start, let's define arrays. An array is a data structure that stores a collection of elements in contiguous memory locations. Each element can be accessed directly by its index. Arrays can be either fixed in size, known as static arrays, or capable of dynamic resizing in languages that support dynamic arrays. On this slide, you'll see an illustration that shows an array structure along with its indices 0, 1, 2, and so on to help solidify this concept. Next, we'll dive into time complexity. Time complexity measures how the runtime of an algorithm increases as the input size grows. We use big O notation to describe the worst-case scenario for an algorithm's performance. In the context of arrays, this is particularly important for deciding which operations to use and how to optimize them. For example, accessing an element by index is O(1), which means it takes constant time, while searching through an array might take O(n) time. Please refer to the animation on this slide that shows constant time and linear time operations. Now, let's review some common array operations and their corresponding time complexities. Access, retrieving an element by its index takes constant time, or O(1). Insertion, inserting an element at a specific position can take O(1) time at the end of the array, amortized in dynamic arrays, but might take O(n) time in the worst case if shifting is required. Deletion, removing an element from a specific position generally costs O(n) time due to the need to shift remaining elements. Search, finding an element in an unsorted array typically has a time complexity of O(n). On this slide, there is an animation that visually shows all the scenario of these operations alongside their time complexities. Let's compare arrays to other data structures to understand their strengths and weaknesses. Arrays versus linked lists. Arrays allow O(1) access time, while linked lists typically require O(n) time for access. However, linked lists may offer faster insertions and deletions in certain cases. Arrays versus hash tables and trees. Each data structure has different trade-offs regarding speed and memory usage. Arrays are especially useful in scenarios where frequent random access is required or when the number of elements is known ahead of time. To summarize, arrays provide constant time, O(1) access, which is ideal for random access operations. Insertion and deletion operations in arrays typically incur an O(n) cost when shifting is needed. Understanding these time complexities is crucial in choosing the right data structure for a given problem. I now invite any questions you may have or any discussion points regarding optimizing array operations. Please send me the question and comment section of this video. I will be happy to answer. On this note, I am stopping over here. See you in the next session.